Our universe consists of billions of galaxies, each teeming with stars and planets, all encapsulated within the observable limits that our current technologies allow us to see. But what lies beyond this boundary? In this documentary, we embark on a journey beyond the edge of the observable universe. We begin by understanding the observable universe itself, its size, scope, and the limits of our current observations. We delve into the theories that hint at what lies beyond, the concept of the multiverse, string theory, and the possibility of extraterrestrial life. We will explore the mysteries of dark matter and dark energy, entities that dominate our universe yet remain largely invisible and unknown, as well as the potential existence of parallel universes and alternate dimensions, challenging our understanding of space, time, and our place within it all. Join us as we push the boundaries of our knowledge, exploring the greatest mystery of our time. What is outside the observable universe? The observable universe, a term that sparks intrigue and wonder, encapsulates everything that we can see or detect from Earth using our current technology. It is defined by the farthest reaches of space from which light has had time to travel to us since the beginning of the universe, approximately 13.8 billion years ago. This does not mean the universe is 13.8 billion years in diameter. Rather, due to the expansion of the universe, it's estimated to be about 93 billion light-years across. This vast expanse contains all the galaxies, stars, planets, and other celestial objects that we can observe. In the center of this cosmic expanse lies a principle that governs our understanding: the speed of light, a constant at about 299,792 kilometers per second in a vacuum. This universal speed limit sets the boundaries of our observable universe. When we look at a star that is, say, 1,000 light-years away, we're seeing it as it was 1,000 years ago because that's how long it took for the light to reach us. This means observing the cosmos is also a journey back in time, peering into the history of the universe itself. The observable universe is not static, but is constantly changing. As light from more distant regions reaches us, our cosmic horizon expands. However, due to the universe's accelerated expansion, there are regions whose light will never reach us. These areas lie beyond our observable universe. This expansion is driven by dark energy, a mysterious force that constitutes about 68% of the universe's total energy and acts contrary to the gravitational pull of matter. Scientists study the observable universe through advanced telescopes that not only detect visible light, but also other forms of electromagnetic radiation, such as radio waves, infrared, and X-rays. This multi-wavelength observation allows us to uncover the universe's hidden aspects, like the cosmic microwave background radiation, a relic from the universe's infancy, providing clues about its earliest moments and expansion. The composition of the observable universe is another fascinating aspect. It is mostly empty space, with galaxies, including our Milky Way, scattered throughout like islands in an immense ocean. These galaxies host a myriad of stars, many of which have planets orbiting them. It's estimated there are more stars in the observable universe than grains of sand on all of Earth's beaches combined, a testament to the universe's unfathomable scale. Measuring the extent of the observable universe is a task involving not just astronomical distances, but also the age of the universe itself. Scientists employ a variety of methods to gauge these vast expanses, each method a testament to human ingenuity in peeling back the layers of cosmic mystery. At the core of these endeavors is the understanding of light-year distances, a concept that represents the distance light travels in 1 year, roughly 9.46 trillion kilometers. This measure serves as a cosmic yardstick, allowing astronomers to navigate the vast reaches of space. One pivotal tool in the astronomer's arsenal is the observation of type Ia supernovae. These stellar explosions serve as standard candles due to their consistent luminosity, allowing scientists to estimate distances based on how bright these supernovae appear from Earth. By calculating the light's redshift, a phenomenon where light stretches into longer, redder wavelengths as it travels across the expanding universe, astronomers can deduce the rate at which the universe is expanding and, consequently, estimate its size. Furthermore, the cosmic microwave background radiation, a faint glow left over from the universe's infancy, provides a cornerstone for measuring the observable universe. This radiation presents a snapshot of the cosmos merely 380,000 years after the Big Bang, its uniformity and minute fluctuations helping scientists infer the universe's overall geometry and expansion rate. These observations, combined with sophisticated models of the universe's expansion, allow for calculations that estimate the observable universe's extent. Advancements in technology have significantly bolstered these efforts. Telescopes, both ground-based and in space, equipped with advanced sensors and cameras, capture light across various wavelengths, from radio waves to gamma rays. This multispectral observation enables a more nuanced understanding of cosmic distances, revealing objects and phenomena not visible in the traditional optical range. It's also through the diligent application of Einstein's theories of relativity, which offer predictions about the universe's structure and dynamics, that scientists can refine their measurements of cosmic distances. These theories help explain how gravity bends light, a phenomenon known as gravitational lensing, which astronomers can use to measure the mass of galaxy clusters and infer distances across the universe. Venturing beyond the edges of our observable universe into places where light has not had the time to reach us since the universe's birth lies a tapestry of cosmic mysteries and theoretical wonders. These regions, unreachable by our current observational technologies, hold the promise of unraveling fundamental questions about the universe's very nature and its ultimate fate. Just beyond our observational reach, cosmologists speculate about the existence of other galaxies, stars, and perhaps even variations of physical laws or constants that could drastically differ from our own corner of the cosmos. The concept of the multiverse, a theory suggesting the existence of multiple, perhaps infinite universes with varying properties, teases the imagination. Each of these universes could harbor unique physics, different forms of matter, and alternative versions of reality, challenging our understanding of existence itself. In these unobservable regions, dark matter and dark energy, two of the most profound mysteries in cosmology, continue to perplex scientists. While we can infer their presence from gravitational effects and the universe's accelerating expansion respectively, their true nature remains hidden. Beyond our observable limits, these components could exhibit behaviors or properties that provide keys to unlocking their mysteries, potentially reshaping our understanding of the universe's structure and dynamics. Another tantalizing question is the very shape and extent of the universe. Is it infinite, looping back on itself in an unimaginable curvature? Or does it have a boundary beyond which lies what? Theories abound, but without the ability to observe these regions, they remain speculative, a frontier of human curiosity and scientific inquiry. Moreover, the possibility of life beyond our observable universe ignites both scientific and philosophical debate. If conditions suitable for life exist in our observable cosmos, what about beyond? The potential diversity of life, governed by different physical laws or constants, expands the scope of astrobiology into realms of pure conjecture, but with profound implications for understanding life's place in the cosmos. The cosmic microwave background radiation, our universe's afterglow from the Big Bang, offers a glimpse into the infant universe, but also hints at what lies beyond our observable limits. Tiny fluctuations in this radiation could be markers of processes or objects in the unobservable universe, indirectly impacting what we can see. In the realms beyond the observable, scientists theorize the potential for physical laws or constants to differ from those we know. This variance could give rise to elements or forces unfamiliar to us, challenging the standard model of particle physics that currently provides the foundation for our understanding of the universe's workings. The standard model, while remarkably successful in explaining the particles and forces within our observational reach, acknowledges its limitations, suggesting the existence of phenomena yet to be discovered. Cosmological models and theories, such as string theory and the concept of a multiverse, provide frameworks within which these unknown elements or forces could exist. String theory, for instance, posits the existence of additional dimensions beyond our familiar 3 spatial dimensions and 1 temporal dimension. In these extra dimensions, forces and particles unknown to current science could operate, potentially influencing the universe in ways we have yet to comprehend. The intriguing possibility of dark matter and dark energy, substances that constitute about 95% of the total mass energy content of the universe but remain enigmatic, hints at the kinds of unknown forces or elements that might exist. These phenomena suggest that our understanding of gravity and the fundamental forces could be incomplete, pointing to the potential for new physics lying just beyond our reach. In the uncharted territories beyond our observational reach, the cosmos may harbor theoretical particles that elude our current understanding and detection methods. These hypothetical entities, posited by physicists to explain phenomena not fully accounted for by the standard model of particle physics, stir the imagination and drive the quest for a more complete theory of the universe. One of the most intriguing categories of these theoretical particles is dark matter candidates, which include WIMPs, weakly interacting massive particles, and axions. WIMPs, massive particles that interact weakly with other matter, are thought to make up a significant portion of the universe's mass, revealing themselves not through light, but by their gravitational influence on galaxies and galaxy clusters. Axions, much lighter than WIMPs, are hypothesized to solve the strong CP or charge parity problem in quantum chromodynamics and might also contribute to the dark matter composition. Another speculative set involves supersymmetric particles or sparticles predicted by supersymmetry, a theory proposing a partner particle for every particle in the standard model. These partners would differ in spin, a fundamental characteristic of particles, and could include neutralinos and gravitinos, both candidates for dark matter. Supersymmetry aims to bridge the gap between the standard model and the theory of general relativity, providing a pathway to a grand unified theory of physics. The theoretical framework of string theory suggests the existence of vibrational modes of strings, each mode representing a different particle. These strings, vibrating at distinct frequencies, could account for all fundamental particles and forces, suggesting a plethora of yet undiscovered particles that could reside beyond our observational capabilities. Prions, another theoretical group, are hypothesized to be subcomponents of quarks and leptons, the building blocks of matter. If proven to exist, prions would signify a deeper layer of subatomic structure, offering insights into the composition of matter at an even more fundamental level. Superstring theory, a fascinating topic in theoretical physics, offers a radical reimagining of the universe's fabric, extending our conceptual reach far beyond the observable cosmos. At its core, superstring theory posits that the most fundamental constituents of the universe are not point-like particles, as traditionally conceived, but rather tiny, vibrating strings. The vibrational patterns of these strings determine the particle's characteristics, such as mass and charge, weaving together the tapestry of everything we observe. In this paradigm, space and time themselves undergo a profound transformation in conceptualization. Superstring theory introduces additional dimensions beyond our familiar three-dimensional space and one-dimensional time. While this might sound like the stuff of science fiction, in superstring theory, these extra dimensions are not expansive realms, but are instead compactified, folded into the fabric of the universe at scales so small they elude our current observational capabilities. The implications of superstring theory for understanding space beyond the observable are manifold. Firstly, it suggests that the universe at its most fundamental level is unified, with all forces and particles emerging from the same foundational entities, strings. This unity provides a potential bridge between the seemingly incompatible realms of quantum mechanics and general relativity, offering a glimpse into a theory of everything that could describe all physical phenomena under a single framework. Moreover, the extra dimensions posited by superstring theory could fundamentally alter our understanding of cosmic phenomena. These dimensions might harbor the forces and particles that interact in ways invisible and undetectable in our three-dimensional perspective, possibly explaining the mysteries of dark matter, dark energy, and other phenomena that challenge current scientific paradigms. The question of whether the universe is infinite remains one of the most profound and elusive inquiries within cosmology. An infinite universe suggests an endless expanse of space, containing an unbounded number of stars, galaxies, and potentially even parallel versions of our own cosmic neighborhood. This notion challenges not just our understanding of the cosmos, but also our philosophical and existential frameworks. If the universe is indeed infinite, it would mean that the cosmos extends far beyond the observable universe, the region of space from which light has had time to reach us since the Big Bang. The observable universe, about 93 billion light-years in diameter, is but a speck within this unfathomable expanse. In an infinite universe, the implications for cosmology and fundamental physics are profound. It would suggest that cosmic structures and phenomena repeat endlessly, given the infinite canvas of space, leading to the possibility of an infinite number of Earth-like planets, and, by extension, potential life forms. Infinity also raises intriguing questions about the distribution of matter and energy in the cosmos. According to the cosmological principle, the universe on a large enough scale is homogeneous and isotropic, meaning it looks the same in all directions and from all points. In an infinite universe, this principle would imply an endless repetition of large-scale structures, such as galaxies and clusters of galaxies across the cosmos. However, the concept of infinity does not sit easily within current physical theories. For instance, if the universe contains an infinite amount of energy, it would challenge our understanding of conservation laws and thermodynamics. Moreover, the idea of an infinite number of exact copies of our own planet, each with minor variations, confronts us with philosophical dilemmas regarding identity, uniqueness, and the nature of reality. On the practical side, the notion of infinity complicates the task of cosmologists. If the universe is indeed infinite, it means we can only ever observe a finite part of it, bounded by the speed of light and the age of the universe. This limitation means we may never fully comprehend the universe's scale, structure, and ultimate fate, as vast regions will forever remain beyond our observational reach. Diving into the concept of cosmic inflation, a period of rapid expansion shortly after the Big Bang, unveils a cosmos teeming with possibilities, especially when we ponder what lies beyond the observable universe. Cosmic inflation, proposed by physicist Alan Guth in the 1980s, suggests that the universe expanded exponentially within the first fraction of a second of its existence. This theory not only explains the uniformity of the cosmic microwave background radiation, but also posits the existence of phenomena and structures beyond our observational reach that challenge our conventional understanding of space and time. One of the most tantalizing ideas born out of inflationary theory is that of quantum fluctuations. During inflation, tiny quantum fluctuations could have been stretched to cosmic scales, seeding the formation of large-scale structures like galaxies and clusters of galaxies. Beyond the observable universe, these fluctuations could have given rise to vast regions with varying physical constants or even different laws of physics, creating a patchwork quilt of cosmic diversity. Another speculative but intriguing outcome of cosmic inflation is the formation of pocket universes or parallel universes within a broader multiverse. Each pocket universe could potentially harbor vastly different physical characteristics, including variations in the fundamental forces, types of particles, and the nature of physical laws. This concept challenges our understanding of reality, suggesting that our universe might just be one of many bubbles in a cosmic foam, each bubble constituting a separate universe with its own unique properties. Cosmic inflation might also have led to the creation of primordial black holes, formed not from the collapse of stars, but from the intense gravitational forces at play during the universe's rapid expansion. These primordial black holes, possibly populating the regions beyond our observable universe, could hold clues to understanding dark matter and the early dynamics of the cosmos. Additionally, cosmic inflation implies the existence of gravitational waves, ripples in the fabric of space-time caused by the universe's explosive growth. These waves, potentially detectable as subtle patterns in the cosmic microwave background radiation, could provide a direct glimpse into the universe's first moments, offering insights into phenomena occurring beyond our current observational limits. The concept of bubble universes presents a captivating vision of a cosmos filled with myriad separate universes, each encapsulated within its own bubble-like domain. This idea springs from the inflationary model, which posits that the universe underwent a rapid expansion just moments after the Big Bang, stretching space-time and possibly giving rise to countless individual universes within a vast cosmic multiverse. Each of these bubble universes, according to the theory, could be vastly different from our own, containing unique variations of physical laws, particles, and cosmic structures. The genesis of these bubble universes lies in the inflationary field, believed to be responsible for driving the exponential expansion of the early universe. Fluctuations within this field could cause certain regions to stop inflating and cool down, forming pockets where conditions allow for the development of a universe. Meanwhile, the space between these pockets continues to expand, forever isolating them from one another in an ever-growing multiverse. The contents and characteristics of these bubble universes are a subject of rich speculation. In some, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, might differ significantly from those in our universe. Such variations could lead to radically different types of chemistry, or even entirely novel forms of matter and energy, not found in our cosmic neighborhood. The structure of these universes could range from relatively barren, with few galaxies or stars, to densely packed with astronomical objects, depending on the rate of expansion and the nature of physical laws governing them. Furthermore, the idea of bubble universes raises intriguing possibilities regarding the formation of galaxies, stars, and potentially life. In universes where the physical constants are just right, conditions may favor the emergence of complex structures and even living organisms. Conversely, in universes where these constants are vastly different, the development of recognizable structures, let alone life, might be impossible. Detecting these bubble universes directly is beyond our current technological capabilities, as they would lie beyond the observable limits of our universe. However, scientists speculate that indirect evidence might be found in the form of gravitational waves or anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang, which could hint at interactions between our universe and others in the multiverse. Dark matter, a mysterious substance that does not emit, absorb, or reflect light, plays a pivotal role in shaping the cosmos, extending its influence far beyond the confines of the observable universe. Constituting about 27% of the universe's total mass energy content, dark matter's presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Though invisible and elusive, dark matter acts as the cosmic glue that holds galaxies together and drives the formation of the vast web-like structures that define the cosmos. Beyond the observable universe, dark matter is thought to continue its role as the primary architect of cosmic structure. Its gravitational pull is essential for the formation of galaxies and galaxy clusters, even in regions we cannot see. Theoretical models suggest that dark matter's distribution in these unobservable regions would follow patterns similar to those within our observable horizon, forming an intricate cosmic web of dark matter filaments. These filaments would serve as the scaffolding on which visible matter congregates and forms galaxies. In the vast expanses beyond our sight, dark matter could also play a crucial role in the creation of structures that might seem unfamiliar or vastly different from those within our observable universe. Depending on the variations in density and distribution of dark matter, these regions might host unique formations of galaxies, or even types of astronomical objects that are rare or non-existent in the visible universe. The interaction between dark matter and dark energy, the mysterious force driving the universe's accelerated expansion, would further influence the evolution and appearance of these structures. The behavior of dark matter beyond the observable universe could hold clues to understanding its true nature. Current theories propose various candidates for dark matter, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, among others. Observations and models of the universe's structure, both within and beyond our observable limits, provide critical tests for these theories, offering insights into the properties of dark matter particles. Considering the universe beyond the observable, it's conceivable that variations or even unknown forms of dark energy could exist, potentially influencing the universe's expansion in ways we have yet to comprehend. Within our observable universe, dark energy appears to be remarkably uniform, but beyond our observational limits, its properties could vary, leading to regions where the expansion of the universe accelerates at different rates, or even areas where the effects of dark energy are diminished or enhanced. The possibility of such variations introduces fascinating questions about the nature of dark energy itself. Could it be a cosmological constant, a value inherent to the vacuum of space itself, as Einstein once proposed? Or might dark energy be a dynamic field, changing over time and space, akin to dark matter, but with repulsive rather than attractive gravitational effects? Theoretical models, including quintessence, propose that dark energy could be the result of a field that changes in density across the universe. Such a field could lead to observable consequences, potentially offering clues about the nature of dark energy through its impact on the cosmic microwave background radiation or the distribution of galaxy clusters. While direct evidence for the existence of other universes remains elusive due to the limitations of our observational capabilities, several theoretical frameworks suggest ways in which we might infer the presence of a multiverse. One potential indicator of a multiverse could come from the study of the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB is a nearly uniform radiation field permeating the universe, but it contains tiny fluctuations in temperature. Some theories of inflation predict that these fluctuations could be influenced by interactions with other universes. If certain patterns or anomalies within the CMB, such as cold spots or unusually large structures, cannot be explained by standard cosmological models, they might hint at gravitational effects or collisions with other bubble universes. Another avenue of investigation involves the constants of nature, such as the gravitational constant or the fine structure constant. These constants appear to be finely tuned to support the existence of life, a phenomenon often cited in discussions of the anthropic principle. In a multiverse scenario, each universe could have different values for these constants, with our universe's particular set of values being just one of many possibilities. The discovery of theoretical or observational evidence suggesting that these constants could vary across different regions of space-time might support the multiverse hypothesis. The search for dark flow, large-scale patterns of galaxy movements that cannot be explained by the distribution of mass visible to us, could also provide clues. Some researchers speculate that dark flow could be the gravitational pull of other universes on ours. If verified, such patterns would offer indirect evidence of universes beyond our own. Quantum mechanics offers another perspective, particularly through the many worlds interpretation, which posits that all possible quantum events can occur in separate branching universes. While this interpretation is a philosophical approach to quantum mechanics, rather than a direct evidence of a multiverse, advancements in our understanding of quantum phenomena might lead to new ways of inferring the existence of these parallel universes. Finally, the discovery of imprints of other universes could come from high-energy physics experiments, such as those conducted at particle accelerators like the Large Hadron Collider, LHC. The creation of mini black holes, or the detection of particles or forces that do not fit within the standard model of particle physics, might suggest interactions with or the influence of other universes. The idea that alternate universes could operate under different laws of physics ignites the imagination and challenges our understanding of reality. Within this theoretical framework, each universe in the multiverse could have its own set of physical constants and laws, leading to cosmic environments radically different from our own. This divergence in physical laws could manifest in a variety of intriguing and profound ways, reshaping the nature of matter, energy, space, and time across different universes. One of the most fundamental aspects that could vary is the strength of the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In our universe, these forces are finely tuned to allow for the existence of atoms, molecules, stars, and galaxies. In an alternate universe, a stronger gravitational force could lead to stars that are much smaller and burn out more quickly, or a weaker force might prevent the formation of galaxies altogether. Similarly, variations in the electromagnetic force could impact the behavior of charged particles and the formation of chemical bonds, radically altering the chemistry and the potential for life as we know it. The mass of elementary particles, such as electrons and quarks, is another parameter that could differ. In a universe where these particles have significantly different masses, the structure of atoms could change, affecting the complexity and variety of possible chemical elements and compounds. This could lead to a universe with a completely different periodic table, or perhaps a universe where complex chemistry is impossible. The cosmological constant, which is thought to be responsible for the accelerated expansion of our universe, could vary across different universes. In some universes, a much larger cosmological constant could cause such rapid expansion that matter does not have time to coalesce into galaxies and stars, leading to a cold, dark, and empty universe. Conversely, a smaller cosmological constant could result in a universe that collapses back on itself in a big crunch, possibly even cycling through endless expansions and contractions. Alternate universes might also exhibit differences in quantum mechanics, with variations in the principles that govern particle behavior. This could lead to universes where uncertainty, superposition, and entanglement manifest in fundamentally different ways, potentially allowing for novel forms of computation, communication, or energy transfer. As we extend our gaze to the parts of the cosmos that lie beyond our observable limits, the number of worlds that could host advanced civilizations multiplies exponentially, inviting speculation about the nature and extent of life in the universe. The limitations of our current technology confine our observations to the observable universe, a spherical region of space centered around the Earth, from which light has had enough time to reach us since the Big Bang. Beyond this horizon lies the unobservable universe, vast tracts of space whose light has yet to grace our telescopes. The laws of physics as we understand them do not preclude the existence of planets, galaxies, and potentially life forms in these distant realms. If conditions similar to those that fostered life on Earth exist in these regions, it stands to reason that advanced civilizations could have emerged and evolved, possibly developing technologies and modes of understanding far surpassing our own. Moreover, the concept of the multiverse, where our universe is but one of many, each with its own physical laws and constants, further expands the potential for advanced civilizations. In some of these universes, the conditions might be even more conducive to the emergence and development of intelligent life than in our own universe. These civilizations, if they exist, could have explored and understood their universes in ways we can scarcely imagine, potentially even mastering interuniversal communication or travel. The search for extraterrestrial intelligence, SETI, within our observable universe has yet to yield conclusive evidence of advanced civilizations. However, this does not diminish the likelihood of their existence beyond our current observational capabilities. The vast distances and the limitations of our technology present significant challenges to detecting such civilizations. Signals from these distant worlds, whether electromagnetic or other hypothetical forms of communication, would need to traverse immense distances, potentially taking millions or billions of years to reach us, and would require detection capabilities far beyond our current technology. The possibility of advanced civilizations in the unseen cosmos fuels not only scientific inquiry, but also philosophical and ethical considerations about our place in the universe. It prompts us to ponder the nature of such civilizations, their cultures, technologies, philosophies, and how they might have solved challenges that we currently face or will face in the future. The exploration of space, both within and beyond our observable limits, remains one of humanity's most profound endeavors, driven by an innate curiosity and a desire to understand our cosmic neighbors and, ultimately, ourselves. Imagining the technologies that advanced civilizations beyond our observable universe might possess opens a fascinating window into both speculative science and the limits of our current understanding. These civilizations, if they exist and have developed far beyond our technological capabilities, could employ means of observation and communication that seem like science fiction from our current vantage point. One theoretical technology is the use of advanced telescopes or observation devices, far surpassing the power of our current instruments. These devices could potentially manipulate the fabric of space-time itself, allowing them to observe distant galaxies and universes in much higher detail than we can fathom. By bending space-time, these telescopes could bypass the light speed limit that restricts our current observational capabilities, providing real-time images of cosmic events billions of light-years away. Another possibility is the use of quantum entanglement for communication. Quantum entanglement is a phenomenon where pairs or groups of particles interact in such a way that the state of each particle cannot be described independently of the state of the others, even when the particles are separated by a large distance. Advanced civilizations might harness this property to transmit information instantaneously across vast distances, breaking free from the constraints of electromagnetic signal travel times. Such a communication network could enable a civilization to remain cohesive over intergalactic or even interuniversal scales. Wormholes, hypothetical passages through space-time that could create shortcuts for long journeys across the universe, represent another frontier that such civilizations might have mastered. If it is possible to create and stabilize wormholes, as some solutions of general relativity suggest, these could be used for instantaneous travel or communication between distant points in space, effectively rendering the vast distances of the cosmos navigable. Additionally, civilizations far more advanced than ours might utilize a form of energy or matter manipulation that is currently beyond our grasp, such as controlling dark energy or harnessing the energy of black holes. These methods could provide the power needed to fuel these incredible technologies, from powering vast galaxy-spanning telescopes to enabling the construction and maintenance of wormholes or other megastructures for communication and travel. Wormholes, a concept that has fascinated scientists and science fiction enthusiasts alike, are hypothetical passages through space-time that could create shortcuts between distant parts of the universe or even provide gateways to other universes entirely. According to general relativity, the theory that describes the gravitational interaction of matter and energy, wormholes are possible configurations of space-time that can theoretically connect two separate points in space and time, much like a tunnel with two ends in different locations or times. The intriguing possibility that wormholes could connect us to distant parts of the universe opens up visions of interstellar travel that bypasses the vast distances of empty space, allowing for instantaneous or near-instantaneous movement across galaxies. This would not only revolutionize our understanding of travel and communication across the cosmos, but also fundamentally alter our perception of distance and separation. Furthermore, if wormholes could indeed connect to other universes, as some interpretations of quantum mechanics and string theory suggest, they would offer a tangible method of exploring the multiverse, a concept that posits the existence of multiple, perhaps even an infinite number of universes with varying physical laws and constants. Through these connections, we might gain insights into the fundamental nature of reality, exploring firsthand the different physical laws and cosmic landscapes that define these alternate universes. However, numerous challenges and mysteries surround the practical use and existence of wormholes. Theoretical models suggest that keeping a wormhole open would require exotic matter with negative energy density, something not found in the observable universe. This exotic matter would counteract the gravitational pull that would naturally close the wormhole, stabilizing the tunnel long enough for something or someone to pass through. The creation and maintenance of a wormhole, therefore, hinge on materials and energy types that are speculative at best with our current understanding of physics. Navigating or even locating a wormhole, should they exist, poses significant technical challenges. Detecting the entrance to a wormhole would likely involve observing the unique gravitational effects it exerts on surrounding matter and light, a task requiring extremely sensitive instruments and potentially new methods of astronomical observation. The fabric of space-time, a central element of our universe's architecture as described by Albert Einstein's theory of general relativity, continues to be a source of profound mysteries and speculation. While current theories have provided us with a substantial understanding of the cosmos, it's almost certain that there are aspects of space-time that remain beyond our current conceptual grasp, waiting to be uncovered or theorized. These unknown mysteries could fundamentally alter our comprehension of the universe and the laws that govern it. One potential mystery could involve the true nature of dark energy and its impact on space-time. While we observe its effects in the accelerated expansion of the universe, its fundamental characteristics and mechanism remain elusive. There may exist aspects of space-time manipulation or alteration tied to dark energy that we have yet to conceive, potentially allowing for phenomena such as the expansion or contraction of space-time in ways that could alter the fate of the universe. Another area ripe for discovery is the granular structure of space-time at the Planck scale, the smallest scale of the universe, beyond which the concepts of time and space cease to function in the ways we understand them. Theoretical physics suggests that space-time might have a quantum structure at this scale, but the exact nature of this structure and how it gives rise to the space-time continuum we observe at larger scales are profound mysteries. This quantum realm could hold the key to unifying general relativity and quantum mechanics, a goal that has eluded physicists for decades. The possibility of higher dimensions beyond the four, 3 spatial dimensions and 1 temporal dimension we experience, could reveal new mysteries of space-time. These additional dimensions, hypothesized by theories such as string theory, could harbor forces, particles, or entire universes that interact with our own in ways we have yet to understand or detect. The mechanisms by which these dimensions are hidden or compactified, and how they could be accessed or influence our universe, are tantalizing mysteries awaiting theoretical and experimental exploration. The concept of time itself may hold mysteries that challenge our current understanding. While we perceive time as a linear progression, theoretical advancements could reveal new aspects of time. Its potential malleability, its relationship with space under extreme conditions, such as near black holes, or even the existence of phenomena that allow for non-linear temporal experiences or connections. Moreover, the ultimate fate of the universe poses a mystery intertwined with the fabric of space-time. While theories such as the heat death, Big Crunch, or Big Rip provide speculative endpoints based on our current understanding, the actual mechanisms and outcomes could be far different, influenced by aspects of space-time and physical laws that are yet to be theorized or discovered. The universe, with its near-infinite expanse, holds the potential for cosmic structures so vast, so complex, or so fundamentally different from anything we've observed that they challenge our very conceptions of matter, space, and the laws of physics. These hypothetical structures, existing beyond the observable universe's 93 billion light-year diameter, represent the frontiers of cosmic speculation and scientific inquiry. One possibility is the existence of superclusters or hyperclusters, structures that dwarf even the largest known cosmic formations. While our observable universe contains superclusters, massive groupings of galaxies and galaxy clusters, there could exist beyond our sight an even more immense layer of cosmic organization. These hyperclusters might span hundreds of billions of light-years, containing not just galaxies and clusters, but entire webs of superclusters linked in a cosmic lattice of dark matter and energy, shaping the universe's large-scale structure in ways we can barely imagine. Another speculative idea is that of dark galaxies or dark matter conglomerates. These could be vast accumulations of dark matter with little to no ordinary matter, making them nearly invisible to our current detection methods. They could harbor unique forms of dark chemistry, possibly even dark life, operating under physical principles radically different from those in our own universe. The existence of such structures could fundamentally alter our understanding of cosmic evolution and the distribution of matter and energy in the universe. Quantum foam structures, theorized to exist at the Planck scale, the smallest scale of the universe, where classical notions of gravity and space-time break down, could also extend into larger yet unobservable cosmic structures. These would be comprised of fluctuations in the fabric of space-time itself, possibly acting as the seeds for the formation of galaxies and larger structures in ways that current models of cosmic inflation and dark matter do not fully explain. Cosmic strings, theoretical defects in space-time predicted by some models of the early universe, could stretch across the cosmos in loops or lines of immense gravitational pull. Beyond our observable universe, these strings might form intricate networks, warping space-time around them and influencing the formation and distribution of galaxies and clusters along their length in patterns vastly different from anything we've observed. Lastly, the concept of parallel universes or bubble universes, as suggested by the theory of cosmic inflation, implies the existence of an endless ocean of universes, each with its own physical laws, constants, and structures. Within this multiverse, the variety of cosmic structures could be limitless, with some universes containing types of matter, forms of energy, and cosmic architectures so alien to our understanding that they defy description. At the very edge of the observable universe, phenomena occur that stretch the limits of our understanding, challenging our perceptions of cosmology, physics, and the nature of reality itself. This boundary, known as the cosmic horizon, is not a physical edge, but a limit imposed by the finite speed of light and the age of the universe. Light from beyond this horizon has not had enough time to reach us since the Big Bang, rendering these regions beyond our current observational capabilities. However, theoretical physics and cosmology provide insights into what might occur at this frontier of visibility. One phenomenon at the edge of the observable universe is the redshifting of light to an extreme degree, known as cosmological redshift. As the universe expands, light traveling across it stretches, causing the wavelength to increase and shift towards the red end of the spectrum. At the cosmic horizon, this effect is maximized due to the vast distances involved, resulting in light that is so redshifted it becomes nearly, if not entirely, undetectable with current technology. This stretching of light also means that the objects near the edge appear much older and less evolved than those closer to us, providing a glimpse into the universe's infancy. Another intriguing phenomenon is the potential visibility of the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, as it would have appeared from those distant regions. The CMB is a snapshot of the universe when it was just about 380,000 years old, before stars and galaxies formed. Observing the CMB from the edge of the observable universe could offer unique insights into the early universe's properties and the distribution of matter and energy moments after the Big Bang. Additionally, theoretical models predict the existence of structures and objects just beyond our observational reach that could influence the cosmic web's formation and evolution within the observable universe. These include massive clusters of galaxies, superclusters, and large voids, whose gravitational effects might be detectable as subtle influences on the motion and distribution of galaxies near the observable universe's edge. Quantum fluctuations at the time of cosmic inflation might also leave imprints on the very edge of the observable universe. These fluctuations, magnified by inflation, could be the seeds for all cosmic structure. Studying the edge of the observable universe could therefore provide clues to understanding inflationary theory and the quantum origins of the cosmos. Finally, the concept of horizon problem resolution is a phenomenon tied to the uniform temperature of the CMB across the sky. The observable universe's edge might hold clues to this uniformity, suggesting faster-than-light expansion rates in the universe's earliest moments, a period known as inflation. This rapid expansion could have allowed distant regions of space to equilibrate, explaining the CMB's smoothness across vast distances. The quest to understand the universe often brings us to the threshold of the observable and into the realm of speculation about what lies beyond. Among the most intriguing prospects is the detection of unknown signals originating from beyond the observable universe. These signals, inherently mysterious due to their origin from regions we cannot see, could potentially carry information about the early universe, the nature of cosmic expansion, and even the existence of other universes or dimensions. One category of these unknown signals could be gravitational waves. Unlike electromagnetic radiation, light, which is impeded by objects in its path and becomes redshifted over vast distances, gravitational waves travel through the cosmos largely unimpeded, offering a pristine glimpse into the universe's most cataclysmic events. Detected from beyond the observable universe, these waves could inform us about collisions of supermassive black holes in the early universe, phase transitions in the vacuum state of the universe, or even cosmic strings, hypothetical defects in space-time. Another potential source of unknown signals might come from neutrinos. These subatomic particles, with their almost negligible mass and weak interaction with matter, can traverse the universe from the most distant regions. Detecting ultra-high-energy neutrinos from beyond the observable universe could offer clues about the conditions of the early cosmos, revealing processes related to the formation of the first structures or hints of physics that deviate from the standard model. Quantum fluctuations, magnified during the period of cosmic inflation, might also leave imprints detectable as subtle anomalies in the cosmic microwave background, CMB radiation. These imprints could manifest as patterns or cold spots that hint at the influence of structures or phenomena beyond our observable horizon, potentially even signatures from other universes in a multiverse scenario, where bubbles of space-time form distinct universes. Additionally, theoretical constructs like dark matter axions could generate detectable signals. If these hypothetical particles exist and interact with our observable universe from beyond, they might produce unique electromagnetic signatures under certain conditions. Discovering such signals could not only prove the existence of axions, but also offer a window into the larger unseen cosmos. Black holes, some of the most enigmatic entities we know of, serve as cosmic laboratories for testing the limits of physics. Those lying beyond the observable universe, in regions we cannot yet see or study directly, tantalize scientists with the potential to hold secrets about the universe's most profound mysteries. One secret pertains to the nature of quantum gravity. Black holes challenge our understanding by bringing the principles of general relativity, which describes gravity at macroscopic scales, into conflict with quantum mechanics, which describes the microscopic world. Black holes beyond our observable universe might exhibit behaviors or properties that provide insights into this unification problem. For example, the way in which these black holes evaporate through Hawking radiation could offer clues about how gravity operates at quantum scales, potentially leading to a theory of quantum gravity. Another secret involves the formation and evolution of the early universe. Primordial black holes, hypothetical black holes formed soon after the Big Bang through the collapse of density fluctuations, could exist in abundance beyond the observable universe. These objects could inform us about the conditions of the early universe, including the distribution of matter and the nature of dark matter. If primordial black holes contribute significantly to dark matter, detecting their signatures, such as gravitational waves emitted from collisions, could unveil the universe's dark sector's composition and behavior. The information paradox, a puzzle concerning the fate of information that falls into a black hole, also hides secrets about the fundamental principles of the universe. Do black holes beyond the observable universe destroy information, as classical theories suggest? Or is information somehow preserved, as required by quantum mechanics? The resolution of this paradox could revolutionize our understanding of information, entropy, and the fabric of space-time itself. Supermassive black holes beyond the observable universe could reveal the process of galaxy formation and evolution on scales and in environments different from those we can observe. The interaction between these black holes and their surrounding dark matter halos, interstellar gas, and star systems could provide unique insights into the dynamics of galaxy formation in different cosmic epochs and environments. The existence of black holes with properties or behaviors not predicted by current theories could open the door to new physics. This could include black holes in higher dimensional space, as predicted by some theoretical models, or black holes with unusual charge or spin characteristics that challenge our understanding of astrophysical processes. These anomalies could hint at the existence of exotic particles, fields, or principles of physics that only manifest under the extreme conditions present at black hole event horizons. While black holes are well-established objects in cosmology, known for their extreme gravitational pull from which not even light can escape, the idea that they might serve as bridges or tunnels to distant parts of the universe or to other dimensions is grounded more in theoretical physics than in observational evidence. Yet, this notion captivates the imagination and invites exploration into the limits of our understanding of the universe. At the heart of this idea is the theoretical construct known as a wormhole. Wormholes, solutions to the equations of general relativity, are hypothetical tunnels through the fabric of space-time, connecting two distant points in the universe, or potentially linking different universes altogether. In some models, the entrance to a wormhole could resemble a black hole, possessing a horizon beyond which the laws of physics as we know them begin to break down. Theoretical physicists speculate that if wormholes exist, they could, in principle, allow for instantaneous travel across cosmic distances or serve as gateways between different universes in a multiverse framework. However, several formidable challenges stand in the way of this being more than theoretical speculation. For one, the stability of wormholes is a significant issue. Calculations suggest that they would collapse too quickly for anything to travel through unless they are kept open by a form of exotic matter with negative energy density, something that has yet to be discovered or understood. The very notion of traveling through a black hole to emerge in another part of the cosmos or a different dimension confronts us with the problem of singularity. At a black hole's core, according to current theories, lies a point of infinite density, where the laws of physics no longer apply as we know them. How matter or information could pass through this singularity intact is a profound mystery, one that challenges our current understanding of physics. The early universe, a period just after the Big Bang, holds crucial clues about the cosmos that extends beyond the observable limits. This primordial epoch, encapsulated in the cosmic microwave background radiation, provides a snapshot of the universe when it was only 380,000 years old. By studying the CMB, scientists gain insights into the conditions that prevailed in the early universe, offering hints about the vast cosmos that lies beyond our current observational capabilities. One of the key clues from the early universe is the uniformity of the CMB across the sky. This surprising uniformity suggests that different regions of the universe, even those that are not causally connected, meaning light has not had time to travel between them since the Big Bang, have similar temperatures. This observation has led to the inflation theory, which posits that the universe underwent a rapid expansion shortly after its birth, smoothing out any initial irregularities. Inflation implies that the regions beyond our observable universe were once connected to our own, and therefore might share some of its fundamental properties. This connection hints at a cosmos that is homogeneous on the largest scales, extending far beyond what we can see. The quantum fluctuations that occurred during inflation are another crucial clue. These tiny variations in density, magnified by the inflationary expansion, became the seeds for all future structure in the universe. Galaxies, clusters of galaxies, and the vast cosmic web. Observing these fluctuations in the CMB provides a direct link to the processes occurring in the very early universe, suggesting that similar structures could exist throughout the cosmos, even in parts we cannot observe. The distribution and nature of these fluctuations can inform models of cosmic inflation, offering insights into the physics governing the universe at its most fundamental level. The early universe's clues about dark matter and dark energy, two of the most mysterious components of the cosmos, extend our understanding beyond the observable. The way galaxies and galaxy clusters formed and evolved under the influence of dark matter, observable in the CMB's slight anisotropies, implies that dark matter's presence and properties are consistent throughout the cosmos. Similarly, the accelerated expansion of the universe, attributed to dark energy, affects the fabric of the entire cosmos, suggesting that the dynamics of dark energy observed within our cosmic horizon apply universally. The study of primordial elements, such as helium and lithium, formed during the first few minutes after the Big Bang in a process known as nucleosynthesis, offers additional clues. The relative abundances of these elements, consistent with predictions across observable regions, support the idea of a uniform set of physical laws and conditions extending throughout the universe, including beyond our observable limits. Lastly, gravitational waves, ripples in the fabric of space-time generated by violent cosmic events, or even the initial moments of the universe itself, carry information about the very early universe that could extend to the unobservable cosmos. Detecting these waves from the infant universe could unveil phenomena or structures in the cosmic landscape beyond our current reach. During the first fractions of a second after the Big Bang, the universe underwent a phase of rapid expansion known as cosmic inflation. This exponential growth stretched the fabric of space-time, smoothing out any initial irregularities and creating a remarkably homogeneous universe on large scales. This inflationary period is pivotal because it determined the large-scale structure of the entire cosmos, including regions far beyond our observable limits. It suggests that the vast expanse of the universe, even the parts we cannot see, shares a common origin and was subject to the same rapid expansion, laying down a uniform foundation across the cosmos. The quantum fluctuations that occurred during inflation also played a crucial role. These tiny variations in density were amplified by the inflationary expansion, becoming the seeds for all future cosmic structures from galaxies to superclusters. The distribution and evolution of matter in the universe's distant regions likely trace back to these initial fluctuations, meaning the large-scale structure we observe in the cosmos has its roots in the quantum-scale physics of the universe's first moments. Additionally, the synthesis of primordial elements, hydrogen, helium, and traces of lithium and beryllium occurred within minutes after the Big Bang during a period known as Big Bang nucleosynthesis. The relative abundances of these elements, determined by the conditions and processes in the universe's first moments, would be consistent throughout the cosmos, affecting the chemical composition of stars and galaxies in even the most distant regions. The imprint of these first moments is also potentially observable in the cosmic microwave background radiation, which permeates the entire universe. Variations in the CMB's temperature and polarization could carry information about the inflationary epoch and the universe's initial conditions, influencing the structure and evolution of cosmic regions far beyond our direct observation. Finally, the distribution and nature of dark matter and dark energy, which together make up about 95% of the total content of the universe, were influenced by the universe's initial state. These mysterious components govern the universe's expansion and structure formation, impacting the development of cosmic regions across all scales and distances. The known universe, with its myriad forms from spiral to elliptical, lenticular to irregular, already presents a vast catalogue of galactic structures. Yet, the potential for undiscovered types of galaxies that could exist in the universe's most distant or hidden regions is a topic ripe for speculation and wonder. One potential category could be ultramassive galaxies, far exceeding the size and mass of any galaxies observed thus far. These hypothetical behemoths would dwarf even the most massive galaxies we know, containing trillions of stars and spanning hundreds of thousands of light-years across. Their formation and evolution would challenge our understanding of cosmic structure and the limits of galaxy formation. Another speculative type could be dark galaxies, composed almost entirely of dark matter with very few, if any, stars. These galaxies would be nearly invisible to our current detection methods, which rely heavily on the light emitted by stars. Dark galaxies could provide critical insights into the nature of dark matter and the role it plays in the structure and dynamics of the cosmos. Galaxies with unconventional forms resulting from unique or extreme conditions might also exist. These could include galaxies with highly irregular shapes not fitting into our current classification schemes, or galaxies that have undergone unusual evolutionary paths due to their environment, such as intense gravitational interactions with neighboring galaxies or exposure to extreme radiation. Primordial galaxies from the very early universe, significantly different in composition and structure from those formed later, could offer glimpses into the cosmos's infancy. These galaxies, likely smaller and less organized than their modern counterparts, would contain stars made almost entirely from hydrogen and helium, the universe's first elements. Their detection would provide invaluable information about the universe's first generations of stars and the conditions that prevailed shortly after the Big Bang. The possibility of mirror galaxies, stemming from the speculative theory of a parallel universe or a mirror world with its own set of physical laws, opens up fascinating avenues for exploration. While entirely hypothetical, these galaxies would be composed of mirror matter, interacting with our known universe in fundamentally different ways, potentially observable through indirect gravitational effects or unusual cosmic phenomena. In the pursuit of observing beyond the cosmic horizon, scientists and engineers are pushing the boundaries of technology, developing new instruments and methodologies designed to peer deeper into the universe than ever before. These technologies aim not only to enhance our view of the distant cosmos, but also to potentially reveal regions that lie beyond the observable universe as we currently understand it. One of the forefront technologies is the next generation of extremely large telescopes, both ground-based and space-based. Ground-based observatories like the Extremely Large Telescope, ELT, being constructed in Chile, and the 30-meter telescope, TMT, planned for Hawaii, aim to have mirror diameters of around 30 to 40 meters, significantly larger than any current telescopes. These telescopes will be capable of collecting more light from faint, distant objects, allowing astronomers to study the earliest galaxies and stars in unprecedented detail. The James Webb Space Telescope, JWST, launched in December 2021, represents the pinnacle of space-based observatories, with its large mirror and instruments designed to observe the universe in infrared light, penetrating through dust clouds and revealing galaxies formed shortly after the Big Bang. Advancements in radio astronomy are also pivotal in extending our observational reach. Projects like the Square Kilometre Array, SKA, an international effort to build the world's largest radio telescope, will use thousands of dishes and up to 1 million low-frequency antennas that will be spread over vast distances. This will enable the SKA to detect extremely faint radio waves from the cosmic dawn, the era when the first stars and galaxies formed, shedding light on the structure of the early universe. Another promising technology involves gravitational wave observatories. Facilities like LIGO and Virgo have already opened a new window onto the cosmos by detecting gravitational waves from colliding black holes and neutron stars. Future projects, such as the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory planned by ESA, aim to detect waves from a wider range of sources, potentially including the primordial gravitational waves generated in the universe's first moments. These observations could offer direct evidence of cosmic inflation, allowing us to probe the physics of the very early universe. Additionally, the development of neutrino observatories, like the IceCube Neutrino Observatory at the South Pole and proposed future projects, aim to detect high-energy neutrinos from cosmic phenomena. Neutrinos, nearly massless particles that rarely interact with matter, can escape from dense regions of space and carry information about events and structures far beyond the reach of electromagnetic radiation. Advances in computational astrophysics and the development of sophisticated algorithms and simulations play a crucial role in extending our understanding of the cosmos. By combining observational data with theoretical models, scientists can simulate the evolution of the universe from the Big Bang to the present day, exploring scenarios and structures that lie beyond our direct observational capabilities. One of the primary ways quantum computing could aid in our exploration is through the simulation of cosmic phenomena. The universe is governed by the laws of quantum mechanics at its most fundamental level, from the interactions within the cores of stars to the behavior of particles in the early universe. Quantum computers, operating on similar principles, could simulate these processes with unprecedented accuracy. This means we could model the conditions of the Big Bang, the formation of the first stars and galaxies, and even predict the behavior of dark matter and dark energy, mysteries that remain beyond our current understanding. Quantum computing could dramatically enhance our ability to process astronomical data. The next generation of telescopes and observatories, both ground-based and in space, will generate vast quantities of data far beyond the capacity of today's classical computers to analyze efficiently. Quantum computers, with their ability to perform multiple calculations simultaneously, could sift through this data more effectively, identifying patterns and signals that might be missed otherwise. This could include the detection of faint signals from the cosmic microwave background radiation or gravitational waves that carry information about the universe's earliest moments, potentially revealing aspects of the cosmos that lie beyond the observable universe. Quantum computing also holds promise for improving our understanding of the large-scale structure of the universe. The cosmic web, a complex network of galaxies, gas, and dark matter, spans the entire observable universe. Simulating the formation and evolution of this structure requires solving numerous equations that describe the interaction of gravity, dark matter, and baryonic matter over billions of years. Quantum computers, with their superior processing power, could tackle these simulations with greater detail and over larger scales, helping us to understand how the universe's largest structures came to be and how they might extend beyond the observable limits. The field of quantum cryptography could secure the transmission of data between Earth and spacecraft, or between telescopes distributed across the globe or in space. This would ensure the integrity of the vast amounts of data collected in our exploration of the cosmos, protecting it from interference or corruption. In theorizing about life in other parts of the universe, scientists often refer to the concept of the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. However, life existing outside our observable universe might not be constrained by such Earth-centric criteria. Instead, it could thrive in environments with alternative solvents to water, such as liquid methane or ammonia, which have been proposed as mediums for biochemical processes under different temperature and pressure conditions. Titan, Saturn's largest moon, with its lakes of liquid methane and ethane, provides a glimpse into how such alternative biochemistries might function. Moreover, life in these unobservable regions might not even rely on chemistry as we know it. It could be based on entirely different interactions, perhaps even utilizing dark matter or energy in ways we cannot currently comprehend. The study of extremophiles on Earth, organisms that thrive in conditions once thought to be uninhabitable, from deep-sea hydrothermal vents to acidic hot springs, already challenges our understanding of life's resilience and adaptability. This resilience suggests that life could find a foothold in a wide array of environments, possibly even those in distant, unobservable parts of the universe where conditions differ markedly from Earth. The exploration of exoplanets, potentially habitable planets that orbit stars outside our solar system, has become one of the most dynamic and rapidly evolving fields in astronomy, offering new insights into the universe's vastness and the potential for life beyond Earth. Since the discovery of the first exoplanets in the 1990s, the number of known exoplanets has soared into the thousands, thanks to advances in detection techniques and dedicated missions such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. Exoplanets vary widely in size, composition, and environment, ranging from gas giants many times the size of Jupiter to rocky worlds that may resemble Earth. Their discovery has revolutionized our understanding of planetary systems, revealing a diversity that was previously unimaginable. We've encountered hot Jupiters, giant planets orbiting perilously close to their parent stars, super-Earths, rocky planets larger than Earth but smaller than Neptune, and even rogue planets drifting through the galaxy unattached to any star. The detection methods employed to find these worlds are ingenious in their application of physics and astronomy. The transit method, for example, looks for dips in a star's brightness as a planet crosses in front of it from our perspective, while the radial velocity method detects the slight wobbles in a star's motion induced by the gravitational pull of orbiting planets. These techniques, among others, have not only expanded our catalogue of exoplanets, but have also allowed astronomers to infer their masses, sizes, compositions, and even atmospheric conditions. Of particular interest are exoplanets located in their star's habitable zone, the region where conditions might be right for liquid water to exist on a planet's surface. Planets such as Kepler 186f and TRAPPIST-1e have captured the imagination of scientists and the public alike, as they represent the best candidates for hosting life as we understand it. Research into these worlds involves multidisciplinary efforts to model their atmospheres, climates, and potential biosignatures, the chemical markers that could indicate the presence of life. The next generation of telescopes, both ground-based and in space, promises to bring us even closer to answering the age-old question of whether we are alone in the universe. The James Webb Space Telescope, with its unparalleled sensitivity to infrared light, is poised to offer detailed observations of exoplanet atmospheres, searching for water vapor, carbon dioxide, methane, and other molecules that might suggest the planet is habitable or even inhabited. Proxima b, orbiting the closest star to our solar system, Proxima Centauri, represents one of the most intriguing exoplanets discovered to date. Located just over 4 light-years away in the constellation of Centaurus, this Earth-sized exoplanet was first announced in 2016, igniting excitement and speculation about its potential for hosting life. Proxima b orbits within the habitable zone of its parent star, where conditions might allow liquid water to exist on its surface, a crucial ingredient for life as we know it. With a mass estimated to be at least 1.17 times that of Earth, Proxima b is thought to be a rocky planet, similar in composition to our own world. Its orbit around Proxima Centauri is remarkably close, with a year on Proxima b lasting approximately 11.2 Earth days. Despite this proximity, the planet receives about 2/3 of the energy from its star that Earth gets from the Sun, owing to Proxima Centauri's status as a red dwarf, a star much smaller and cooler than the Sun. The habitable zone's location around such a star is a double-edged sword. While it allows for the possibility of liquid water, red dwarfs like Proxima Centauri are known for their stellar flare activity, which could pose significant challenges to the potential habitability of Proxima b. These flares can be powerful enough to strip away a planet's atmosphere, leaving its surface exposed to harmful radiation. However, if Proxima b possesses a strong magnetic field, it could protect its atmosphere from these effects, maintaining the conditions necessary for liquid water. The study of Proxima b is at the forefront of exoplanet research, with astronomers using cutting-edge techniques to learn more about its atmosphere, surface conditions, and potential for supporting life. Observations from the next generation of telescopes, such as the James Webb Space Telescope, are eagerly anticipated. These instruments could provide insights into the composition of Proxima B's atmosphere, searching for markers such as water vapor, oxygen, and methane that could indicate the presence of biological processes. Proxima B's discovery has also reignited interest in the search for life beyond our solar system, and has highlighted the potential for future robotic missions, or even interstellar probes to closely study proximal exoplanets. While the challenges of such missions are immense, the allure of discovering signs of life on a planet orbiting our nearest stellar neighbor continues to inspire both scientific inquiry and the imagination of people worldwide. As our observational capabilities expand, Proxima B remains a symbol of the possibilities that lie within our cosmic neighborhood, serving as a reminder of the universe's vastness and the ongoing quest to understand our place within it. Whether Proxima B is habitable or even inhabited remains to be seen, but its discovery represents a significant step forward in our exploration of our universe and its beyonds. Beyond the limits of our current observational capabilities, the universe could be teeming with cosmic catastrophes of immense scale and power, events so profound that they could significantly affect the structure of the cosmos itself. These potential catastrophes range from the familiar, extrapolated to scales and frequencies beyond our direct knowledge, to the speculative, grounded in our understanding of physics yet unobservable in our current epoch or location in the universe. One such event is the collision of supermassive black holes. When galaxies merge, their central black holes are destined to meet, resulting in a cataclysmic release of energy that could warp the fabric of space-time itself. While the gravitational waves from such events might eventually ripple through our part of the cosmos, the immediate vicinity of the collision could experience dramatic changes in gravitational forces, potentially disrupting star systems and altering the course of galactic evolution. Gamma-ray bursts, GRBs, the most energetic explosions known in the universe, could occur with alarming frequency in regions dense with star formation. These bursts of gamma radiation, thought to result from the collapse of massive stars or the merger of neutron stars, can release as much energy in a few seconds as our sun will over its entire lifetime. If occurring close enough to life-bearing planets, GRBs could strip away atmospheres and irradiate surfaces, extinguishing any chance of life. Beyond our observable universe, such phenomena could be shaping the fate of countless worlds. Vacuum decay is a theoretical disaster that posits the existence of a more stable vacuum state to which our current vacuum could transition. If triggered, this transition could propagate through the universe at the speed of light, restructuring the fundamental constants and forces as it goes, rendering the laws of physics as we know them obsolete. Such an event would fundamentally alter the structure of the universe, but whether and where it might occur remains purely speculative. Another speculative catastrophe involves the destabilization of dark matter. If dark matter could be converted into a more stable form under certain conditions, it might release energy on a cosmic scale, affecting the large-scale structure of the universe by altering the gravitational scaffolding that maintains galaxies and clusters. This process could change the face of the cosmos beyond our observation, influencing the distribution and formation of galaxies. The energy release from false vacuum collapses or phase transitions in the early universe could still be echoing through the cosmos, shaping its large-scale structure. These events, akin to cosmic inflation on a smaller scale, could create vast bubbles in which the density of matter and the laws of physics vary slightly, contributing to the universe's patchwork quilt of galactic filaments and voids. Detecting a cosmic event occurring outside the observable universe poses a significant challenge due to the limitations imposed by the speed of light and the finite age of the universe. Since no information can travel faster than light, any event taking place beyond the observable universe's boundary, in essence beyond the reach of the light that has had time to reach us since the Big Bang, is seemingly undetectable using traditional astronomical methods. However, theoretical advancements and indirect methods offer potential pathways for inferring the existence of such events. One potential method involves the study of cosmic microwave background, CMB radiation, the afterglow of the Big Bang, which permeates the universe. Tiny fluctuations in the CMB's temperature and polarization patterns might encode information about the large-scale structure of the cosmos and could potentially reveal imprints of cosmic events or structures beyond the observable horizon. For instance, if a cosmic event caused a large-scale disturbance in the fabric of space-time, it might leave a detectable imprint in the CMB observed today. Gravitational waves offer another avenue for probing beyond the observable universe. These ripples in space-time, predicted by Einstein's theory of general relativity and first directly detected in 2015, can travel through the universe largely unimpeded by matter. Theoretically, gravitational waves generated by massive events, such as the merging of supermassive black holes in the early universe, could traverse the vast distances and reach us from beyond the observable boundary. Advanced gravitational wave observatories, both current and future, may be sensitive enough to detect these waves, offering insights into events occurring in the universe's most distant realms. Quantum entanglement presents a more speculative yet fascinating possibility. This phenomenon, part of quantum mechanics, involves pairs of particles that are interconnected in such a way that the state of one, no matter how distant, instantaneously reflects changes in the state of the other. If a way were found to use entangled particles as messengers of information across cosmic scales, it might, in theory, allow for the detection of events beyond the observable universe. However, leveraging entanglement for such purposes remains a significant scientific and technological challenge. The concept of dark matter and dark energy might also provide clues about the unobservable universe. Understanding how these mysterious components influence the expansion and evolution of the universe could potentially reveal indirect evidence of cosmic events or conditions beyond our current observational limits. Within the universe, numerous unknown forces or phenomena could potentially alter the predicted fate of the cosmos, challenging our current understanding of the universe's evolution. One such enigma is the mysterious nature of dark energy, which constitutes about 68% of the total energy content of the universe. Dark energy is thought to be responsible for the observed accelerated expansion of the universe, a phenomenon that defies the predictions of traditional cosmological models. Understanding the true nature of dark energy and its role in the universe's dynamics is paramount to predicting its fate accurately. If dark energy behaves differently than currently assumed, or if new forms of energy with exotic properties exist, it could significantly impact the universe's future trajectory. Similarly, the nature of dark matter, which comprises about 27% of the universe's total mass energy content, remains poorly understood. While dark matter's gravitational influence is crucial for the formation and evolution of cosmic structures, its exact composition and properties remain elusive. If dark matter interacts with ordinary matter or itself in ways beyond our current understanding, it could lead to unforeseen consequences for the universe's fate. Another potential factor is the existence of unknown fundamental forces or interactions beyond the four known forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Theoretical physics posits the existence of additional forces, such as hypothetical fifth forces, or modifications to existing forces at extreme cosmic scales, which could influence the universe's behavior in unexpected ways. Quantum mechanical effects at cosmological scales, such as those related to quantum gravity, could introduce novel phenomena that alter the predicted fate of the cosmos. Quantum fluctuations in the early universe, for instance, might leave imprints on cosmic structures and influence their evolution over cosmic time. Additionally, the possibility of extra dimensions beyond the familiar three spatial dimensions and one temporal dimension opens up intriguing avenues for speculation. If these extra dimensions exist and have observable effects on cosmological scales, they could introduce new dynamics that reshape our understanding of the universe's fate. The universe consists of multiple unusual yet fascinating anomalies. One such anomaly is the phenomenon of fast radio bursts, FRBs, which are brief and intense bursts of radio waves originating from distant galaxies. While the exact origins of FRBs remain uncertain, their transient nature and high-energy signatures suggest exotic astrophysical phenomena, or possibly even interactions with unknown cosmic entities. Another puzzling cosmic anomaly is the discrepancy between the observed distribution of matter in the universe and predictions based on our understanding of gravity and the known laws of physics. This discrepancy, often referred to as the missing mass problem or the dark matter problem, implies the existence of unseen matter that does not emit or interact with electromagnetic radiation, thus eluding direct detection by telescopes. Anomalies in the cosmic microwave background polarization, rather than its temperature, have raised questions about the early universe's behavior and the nature of cosmic inflation. These anomalies, such as unexpected alignments in the polarization patterns, suggest the possibility of unexplored physics or cosmological mechanisms shaping the universe's evolution. The unexpected behavior of distant galaxies and their motions relative to the cosmic microwave background has puzzled astronomers. Some galaxies appear to be moving at speeds inconsistent with the predictions of standard cosmological models, indicating potential discrepancies in our understanding of the large-scale structure of the universe or the influence of unseen forces at cosmic scales. One very unusual anomaly that has been discovered in the cosmos is the phenomenon known as the Great Attractor. The Great Attractor is a gravitational anomaly located in the direction of the Hydra and Centaurus constellations. It exerts a powerful gravitational pull on galaxies within its vicinity, including our Milky Way galaxy and the galaxies surrounding it. What makes the Great Attractor particularly unusual is that it appears to be drawing galaxies toward it at an unexpectedly high velocity, in defiance of the overall cosmic expansion. This means that galaxies in the vicinity of the Great Attractor are moving faster than what would be expected based on the universal expansion rate. The exact nature and composition of the Great Attractor remain enigmatic, as it is obscured by the dense star fields and dust clouds of the Milky Way. Scientists have proposed various theories to explain this cosmic anomaly, including the presence of a massive concentration of dark matter or the influence of superclusters of galaxies hidden behind the Milky Way. Interstellar travel, the concept of journeying between stars within a galaxy, holds tremendous promise for exploring beyond the observable universe. While our current understanding of physics poses significant challenges to achieving interstellar travel, hypothetical technologies and theoretical concepts offer glimpses into the possibilities of venturing into the cosmos. One key aspect of interstellar travel is the vast distances between stars. Even the closest stars to our solar system are many light-years away, making traditional methods of space travel impractical. However, hypothetical propulsion systems, such as advanced spacecraft propelled by nuclear fusion or antimatter engines, could potentially enable travel at significant fractions of the speed of light. Exploring beyond the observable universe via interstellar travel would allow humanity to study distant stars, planets, and celestial phenomena firsthand. By visiting other star systems, scientists could conduct detailed observations, gather data on exoplanets, and search for signs of life beyond our solar system. Furthermore, interstellar travel could provide opportunities to study cosmic phenomena that lie beyond the reach of our current telescopes. By traveling to different regions of the galaxy, researchers could investigate mysterious objects such as black holes, neutron stars, and exotic astrophysical phenomena that hold clues to the nature of the universe. Concepts like warp drives and faster-than-light (FTL) travel are being theorized as potential means to reach the unobservable cosmos, offering intriguing possibilities for interstellar exploration. These speculative propulsion methods are based on theoretical physics principles that challenge our current understanding of space-time and energy. One such concept is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive theoretically involves warping space-time around a spacecraft, creating a warp bubble that allows the vessel to move faster than the speed of light relative to the surrounding space. Within the bubble, the spacecraft remains stationary, while space-time contracts in front of it and expands behind it, effectively propelling the vessel forward. While the Alcubierre drive offers a compelling solution for faster-than-light travel, it relies on the manipulation of exotic forms of energy with properties not yet observed in nature, such as negative energy or negative mass. Additionally, the immense energy requirements for creating and sustaining the warp bubble pose significant technical challenges. Another theoretical concept for FTL travel involves the concept of wormholes, hypothetical tunnels in space-time that could connect distant regions of the universe. By traversing through a wormhole, a spacecraft could potentially travel vast distances in a short amount of time, effectively bypassing the cosmic speed limit imposed by the speed of light. However, similar to warp drives, the practical realization of wormholes for interstellar travel is hindered by numerous theoretical and technical challenges. These include the stability of wormholes, the existence of exotic forms of matter to stabilize them, and the potential hazards of traversing through them. If we were somehow able to travel beyond the boundaries of the observable universe, it's unclear what we would see, as it ventures into the realm of speculation and theoretical physics. The observable universe represents the portion of the cosmos from which light has had sufficient time to reach us since the Big Bang, approximately 13.8 billion years ago. Beyond this boundary lies regions of space that are currently beyond our observational reach due to the finite speed of light and the expansion of the universe. One possibility is that the universe beyond the observable horizon may exhibit similar characteristics to the observable universe, with galaxies, stars, and other cosmic structures. However, the distribution and arrangement of matter may differ significantly from what we observe within our observable universe, potentially leading to novel phenomena and structures. Another possibility is that the universe beyond the observable horizon could be fundamentally different from our own, with alternate physical laws, properties, and even dimensions. Speculative theories such as the multiverse hypothesis suggest the existence of other universes with distinct properties, potentially governed by different sets of physical constants and laws. If we were somehow able to surpass the limits imposed by the speed of light and travel to these distant regions, our observations would be subject to the effects of cosmic evolution over vast timescales. We might witness the aftermath of cosmic events and phenomena that occurred billions of years ago, offering insights into the history and evolution of the cosmos on a grand scale. The exploration of what lies beyond the observable universe indeed carries significant philosophical implications. One of the central philosophical questions it raises is the nature of existence and our place within the cosmos. The vastness of the universe, both observable and potentially unobservable, prompts contemplation about humanity's significance in the grand scheme of things. The concept of an unobservable universe challenges our understanding of reality and the limits of human knowledge. It confronts us with the realization that there may be aspects of the universe forever beyond our comprehension, highlighting the limitations of our empirical observations and scientific methodologies. Furthermore, contemplating the possibility of multiple universes, as suggested by theories like the multiverse hypothesis, invites reflection on the nature of reality itself. It raises questions about the uniqueness of our universe, the existence of parallel realities, and the potential diversity of physical laws and constants governing different universes. These philosophical inquiries extend to questions about the origins of the universe, the nature of time, and the existence of life beyond our own cosmic neighborhood. They prompt us to re-evaluate our perspectives on existence, consciousness, and the interconnectedness of all things. Scientists are constantly working on missions and experiments to uncover what lies beyond the observable limits of our universe. Particle accelerators like the Large Hadron Collider are crucial in this quest. They recreate conditions similar to those just after the Big Bang, potentially revealing new particles or forces that could help us understand the fundamental nature of the universe. Gravitational wave detectors, such as LIGO and Virgo, have already detected gravitational waves from distant cataclysmic events. Improvements in sensitivity could allow us to detect waves originating from sources beyond our observable universe. Observatories like the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope scan the sky for high-energy phenomena. By studying these events, scientists hope to gather clues about the behavior of matter and energy in extreme environments, providing insights into unobservable regions. Dark matter detection experiments aim to directly detect dark matter particles, which make up a significant portion of the universe's mass. Successful detection could provide indirect evidence of unseen structures and phenomena beyond our current observational limits. Space telescopes like the James Webb Space Telescope, JWST, and the Large Synoptic Survey Telescope, LSST, will capture images of distant galaxies, map the distribution of matter, and study the cosmic microwave background in detail, offering new insights into the nature of the universe beyond what is currently observable. As we end our journey through the depths of the universe, we are left with a profound sense of awe and wonder at the vastness and complexity of the cosmos. Our exploration has taken us to the edges of the observable universe, where we have glimpsed tantalizing hints of what lies beyond. Through the tireless efforts of scientists, engineers, and explorers, we have uncovered mysteries that were once unimaginable. From the enigmatic nature of dark matter and dark energy to the exotic possibilities of wormholes and multiverses, each discovery has brought us closer to unraveling the fabric of reality itself. Yet, as much as we have learned, our journey has also revealed the limits of our knowledge. For every question answered, countless more emerge, challenging us to push the boundaries of our understanding even further. What do you think lies beyond the universe? Is their answer a simple nothing? Or could there be something so vast and unknown that we cannot even comprehend it? Leave your thoughts in the comments below and subscribe to our channel for more documentaries like this. Thanks for watching,